Hello everybody, this is 2017 AMC 12B problem number 22. Here is a view of this combo problem. We have 4 people, A, B, C, D. They play a game. Actually, they will play this game for 4 rounds. And here is the rules of the game. They all start with 4 coins. So we have A, B, C, D. So they initially, initial distribution, initially they all had 4 coins, and they play this game for 4 rounds. 1, 2, 3, 4. Let's do it like this. Okay, so this is round 1, after round 2, round 3, round 4. Let's try to keep track of their coin distributions after each round of playing this game. So how the game is played out. You have an urn with 2 white balls, 1 red and 1 green ball. Apparently those 4 people, A, B, C, D, they all, without replacement, they pull those balls from the urn randomly. And say, for example, that Abby pulls the red one, and let's say Carl pulls the green one, and the other 2 people, Bernardo and Deborah, they pull the white balls. So apparently the rules of the game tells us that whoever gets the green ball gives 1 coin to whoever gets the red ball, right? So in this case, Carl is supposed to give Abby one coin. So Carl will have 1 less coin, and Abby will have 1 more coin. Those who did draw the white ball, they still have the same number of coins. Now we keep playing this game over and over again, and the question says, at the end of the 4th round, what is the probability that each of the players have the same number of coins that they started with? Does that make sense? So we want to play this game again. So what can we do? Well, for instance, one way to do it is I can do the reverse. In the next round, Abby can get the green ball and Carl can get the red ball. In that case, we go back to the original position. And then maybe in the next round, let's say this time Bernardo and Deborah, let's say those 2 people are involved in the transaction, right? One of them picks the red, the other one picks the green. Let's say Bernardo picks the red. In that case, he will have 5. He will have 1 coin transferred from sorry, what am I doing? I'm high. Yeah, so Bernardo picked the red, so he gets 1 coin transferred from Deborah, and the other 2 are 4. But eventually we can do the opposite. On the 4th round, we can have, this time we can have Deborah get the red one, and then Bernardo get the green one, and then boom, we come back to. So it is possible, really. Well, the question is, how many ways can this happen, right? How many different ways? The one that I told you is just one arrangement. Obviously there's quite a lot of arrangements. Well, sorry, the question is asking actually for a probability. So in that sense, the probability would be equal to, right, number of arrangements. Well, when I say arrangements, I mean successful arrangements, obviously. Successful arrangements divided by number of total, all the arrangements. So how many different ways can we assign those 4 balls to these 4 people, right? And when we play this game 4 times, I will just take the 4th power. So if you have 2 white, so we have 2 white and 1 red and 1 green. Well, first of all, how many ways can I give those 2 white to those 4 people? Well, I just choose which 2 of these 4 people will get the white. And then the remaining 2 people, I need to choose who is getting the red, and then the remaining person will automatically get the green, right? So that's 6 times 2, 12 ways. Okay, so I already have my denominator here. Alright, so now how many ways can we successfully run this business? Unfortunately, the way that I created this matrix is not really successful, right? So it's not the best way of arranging this. For instance, the reason I'm telling this is because it's hard to visualize how the transactions takes place and between which 2 people the coin transaction takes place, right? So here we had a transaction, and then going again we had a transaction here plus 1, and then we had a transaction here plus 1, minus 1 if you can see it, and then we had another transaction here minus 1 plus 1. So instead of writing down on our little squares the current number of coins of each individuals, really what we should be focusing more on is the transactions that is taking place, right? Does that make sense? For instance, the one that we have here can be represented in the following way. So let me redraw this picture actually. 1, 2, 3, 4 rounds, and we have A, B, C, D, these 4 people, and then, well, I won't even bother writing the initial arrangements. All I care is the transition, right? What happens in round 1? What happens is this monetary transition. Apparently, Abby is adding 1 coin and Carl is subtracting 1 coin. The other two, there is no transaction. When I go from round 1 to round 2, we have minus 1 for this guy, plus 1 for this guy. And as I go from round 2 to round 3, in round 3, what we're having is plus 1 for Bernardo, and minus 1 for David, or whoever that person is. And then finally the reverse transaction. Hey, that's pretty nice. So this is one arrangement, one successful arrangement. How many successful arrangements can we have like this? So this is a simple case work. Well, when I say simple, don't trust me. Obviously, it can't be simple, right? So it's a number 22 and it's on the AMC 12, you can imagine. So this is the hardest question you can expect on the AMC 10, right? So let's organize our way of thinking. Okay, so here, one thing that bothers me is the naming of these people. Obviously, we need to get rid of this. And then we need to get rid of this as well, right? So therefore, I will not, once I have the main template, if you will, the cases, all I will do is I will count how many different ways I can arrange the columns and the rows, basically. Does that make sense? So therefore, let's begin with the casework then. Let me change this ugly color. Hey, why don't we use green right now? Okay, so here is my first case. So how can these things can happen? Well, one simple idea is the following. So the first case will be the following. I have my 4 columns and my 4 rows. As I said, I won't bother naming the people because eventually I will shuffle them, and I won't bother naming the on which round the transaction took place. But what I have in mind is this. So let's start with the following. Let's say that initially it was, actually I don't even have to write each time plus 1 minus 1, so I can just write plus and minus signs. How about that? Okay, so we can have a transaction between these two people, and I won't even bother writing the zeros. If a square is empty, it means it is 0, right? So let's just focus on the pluses and the minuses. One way to finish this business is I can have plus minus, minus plus. Actually, we can have these two people, whoever those two people are, keep repeating all the transactions, right? That's one successful distribution. So that works, right? So let's count this case quickly. So how many ways can we have this? Well, how many ways can I choose these two guys, which are involved in all the transactions in every single round? So we have 4 people, 4 choose 2 ways we can choose these 2 people, right? So 4 choose 2. That's it. We have already arranged the columns. Now the rows. How many ways can I arrange these rows? So be careful here. We have how many different types of rows do we have? Obviously we have 4 rows, but the answer is not 4 factorial because some of these rows are identical, namely these two, right? These two are identical and these two are identical. So therefore I'm arranging 4 objects, if you will, like A and BB type of, right? So does that make sense? And how many ways can we do that? Hey, this is just like choosing 2 spots for the A's, 4 choose 2 ways again, right? I hope that makes sense. And the final count, 6 times 6. This case produces 36 successful results. Okay, let's go back to our green color. Another case work. How else can this thing happen? Well, I have the following. Obviously, you guys can pause the video here and then try to check your cases. There are actually 3 other types, right? So we should have in total 4 different types. Well, depending on how you classified your thing, and assuming that you don't want to use complementary counting altogether. So you have the people here. These are the guys, and these are the rounds of the game, right? So game rounds of the game again as usual, and here are the contestants. The players, I should say. Yes, the players is a better word. Okay, again I can have plus and minus, then I can have minus and plus, but then in the other 2 rounds, instead of having the same 2 people getting involved, we can have the other 2 people involved, right? How about that? That should work. So how many ways can this happen? Well, okay, so let me get my color. Well, I think in this case, counting, well, okay, so let's start with the players. How many ways can I have? Well, obviously these 2 players are involved in a transaction for these 2 rounds, right? And then those 2 people are involved. So, so therefore, what we want is our 4 guys, our 4 players, A, B, C, D. How many different ways can we place them into 2 buckets where the buckets are indistinguishable? That's important. Indistinguishable buckets. Bucket 1, bucket 1. Huh? How many ways can this happen? Be careful. Yeah, so the answer is not 6. A lot of people would just say 6, right? Because you want to put 2 of them into 1 bucket and then the other 2 into the other, right? So all you do is you can say, hey, the answer is 4, choose 2. Not true. It would have been 4, choose 2 if these buckets were distinguishable, but because they are not distinguishable, the answer is 4, choose 2 over 2, which is 6 over 2, which is 3. Yes, we can arrange the places in 3 different ways. Now, how about the rounds? Well, let's check them carefully. Each of the rows, are they the same or are they all separate? They're all separate, right? We agree. This one is plus minus 0, 0. This one is minus plus 0, 0. This one is 0, 0 plus minus. This one is 0, 0 minus plus. All 4 rows are different. 4 different objects. How many ways can you permute them? In 4 factorial ways. So therefore, this case produces 4 factorial times 3, 24 times 3, 72 successful outcomes. I hope that makes sense. Next case. Case 3. What else can we do? So again, we can start by drawing our matrix, I guess, right? Well, this is not the only way to solve this problem, by the way. Again, we have our players here. You can come up with, well, eventually everything will boil down to casework and a bunch of complementary counting type of arguments. But anyhow, so we start with, there's no harm in starting with plus minus here. Oh yeah, how about that? The first guy is a special guy. In each round, he's involved. But in the remaining 2 rounds, he's involved with someone else. How about that? This is a different case. Does that make sense? So how many ways can this happen? So how many ways can I choose that special guy? 4 ways. All right. How many ways can I choose the other 2 people? In this case, it is these 2 people, right, who are involved with that guy in at least some rounds of transactions. 3, choose 2. This many ways we can arrange the place. 12 ways. Now, how many ways can I arrange the rounds? The rows. Well, are they the same or are they different? They are distinguishable, right? They are all different. 4 factorial ways. You multiply these 2. 12 times 24. Oh, 240 plus 48, 288. Yes. Okay, next. Last case. All right. I need your help on this one, guys. I wish you could have given me feedback. Hey, why don't we pause why don't we stop the recording here, right? And then you finish the problem on your own. And then, well, maybe this would be another type of video formatting. But let's finish this problem. Okay, we've come this far. We can finish it, right? So, okay, the 4 rounds. Can you guys see the remaining case that we haven't considered yet? So please pause the video if You might need to think about it, right? We have our 4 players, the 4 rounds, but these are the names of the rounds. So and then these are right. Okay, and then these are the players. Okay, so plus minus 0 0. Oh, how to do it? Okay, so if I think some of you have guessed it from the beginning, we can make a kind of like a cyclic arrangement, right? And then so in the next round I can make this, in the next round I can do this, and then in the next round, because I can't go further, I can't put the minus here, I need to go back, and then I need to do this. Let's first make sure that everybody ends up in its, yes, so the column sum is 0, so that should work. And in each round we should conserve the number of coins, obviously. Yep, that should work. We're in good shape, people. Let's count it and let's get over with this problem. It's already been almost... I don't know why, I'm getting slower. But anyhow, how many ways can we arrange the players? Are any of the players special? No, sir. 4 factorial ways. That is not true. Okay, that's horribly wrong. I need to divide it by 4, I guess, right? So basically what I'm saying is the first guy, without loss of generality, I can just pick whoever I want, right? Does that make sense? And then, so obviously I'm getting 1 coin here. How many ways can I choose the person who is giving me the coin? In 3 different ways. And then that person in 1 round will get a coin. How many ways can that person, so who can give that? So 2 ways we can choose, and then okay, so therefore it is really 3 factorial, not 4 factorial, my bad. 3 times 2 times 1 here. And how many ways can I arrange the rows? Hey, the rows are all distinguishable. That one is 4 factorial for sure. Okay, so final answer is 4 factorial times 3 times 6. So 4 factorial is 24 times 6 is 144. I have all of my cases. I have 144, 288, 72, and 36. Actually, this is pretty nice numbers. 36, 72, 144, 288. Okay, so I know how to do it. All right, so therefore, final answer, 12 to the power 4, 288 plus 144 plus 72 plus 36, and oh boy. I don't remember the answer. I think the answer was B. I wanna say it's B, and I feel okay, so let's quickly calculate it. So 288 plus 62, what is this? 360? Yeah, that one is 360 plus, and then 144 plus 36 is 180. Okay, so this is 540. Okay, divided by a bunch of 12s. Okay, so we can divide by 4. Ah, that's torture. Okay, so there's a 3 here. If you divide this guy by 4, it's 270, 135. And then we can divide by, obviously, by 3. So I'll have a 4 here. If I divide this guy by 3, I will get a 45. And then I can divide further by 3. Okay, I think I see where we're going, right? So I can divide by 3 and then by 3. So by 9. What did I do here? Okay, yeah, does that make sense? So there's a 5 remaining here. So therefore, final answer 5 over 444. 64 times 3 is, yes, 192. Yes, 5 over 192 is the answer. And we are done in less than 19 minutes. Hope to see you guys in our next lecture.